In this video, we're going to build the plenum and runners for our first K24 intake. Hey everyone, this is Matt with Learn Everything About Design, and welcome to episode 2 of our K20, K24 intake manifold series. Now, as I mentioned in the first video, where we spent quite a bit of time on setting everything up, building out the plates, and just sort of understanding the layout of a design like this, we are going to progress through multiple different intake manifolds. So this first design is going to be using off-the-shelf components that you typically would buy for a DIY type intake. Now, there are a couple of things that we need to consider when we're talking about a DIY intake. Now, the first thing that we need to think about is the size of the plenum. For something like this, there are a handful of manufacturers where you can buy different sizes tubing, and there's really quite a bit out there that can make this process much easier. So there's some links in the description of the video. I'm not associated with any of these companies, so purchase at your own discretion, do some searching. I have purchased mandrel bent tubing from various companies before for intake manifolds and things like that. But again, I'm just putting these links in the description. These are just a couple that I came up with. So there's a company called RMR Racing or Ross Machine Racing. Now they have an eBay store, and I think they have a couple other sites, but they list a handful of very useful bits that you need when you're creating your own intake manifold. Now, some of those are going to be specific to what you're doing. For example, they have oval tubing for the runners, and that's going to be very helpful. It's a little bit larger than we need for a stock K24 port size, but we can also port, so it's something to keep in mind. But they have things like this 5-inch D plenum. So this is pretty handy because it gives us a flat spot that helps us cut the holes for the runners, and it makes it easier for us to fabricate. If we're dealing with a completely round plenum, then it becomes a little bit trickier, especially when we have to cut oval ports, make sure that we have good fitment, and then weld everything together. If you're using a CNC machine or you have some sort of template that you're going to be using to cut, again, this flat makes it very easy. And it's less than $4 an inch. So if you need a runner that is 12 inches long, your investment and the amount of time you save by going with something like this, it can really help. They also have, again, oval runners. Now, I kind of feel like this company is really focused on the 2JZ, specifically 1JZ, 2JZ motors, because everything that they have seems to be sized for that. So the oval runners are a little bit larger than we need. I think the stock port size on the K24 is, when we modeled it, it was about 30 millimeters to 50 millimeters for the oval dimensions. The inside dimensions of these runners are about 31, 32 millimeters to 54 millimeters. So a little bit bigger, but not so large that we can't blend that in our intake plate. So that's something that's very handy to know is how big you can get a runner, or if you can get an appropriately sized runner. Now, once again, keep in mind that when you're purchasing stuff like this, you have to consider the cost. Right now, you can see that it's at $15. The actual plenum was $375 per foot. This doesn't say the length, so I don't know if that's for a 6-foot length, or you'd have to contact them depending on what you need. So again, keep in mind the cost of all this can start to add up. It will be much less than spending $1,000 to $2,000 on purchasing an off-the-shelf intake, and it gives you the option to customize it. So we have the oval runners that are pretty close, but what if the part you're designing doesn't have anything out there that you can purchase? Well, the next step in that process is to buy round tubing and plate and build your own runners. Now, this is something I typically would avoid just because it's really hard to get the pieces to fit just right, depending on the fabrication tools you have. One thing that I have done in the past, not specifically with an intake, but for designing parts like this, is taken a tube or even an oval tube like this and cut a triangle or a notch out of it to taper it down or to widen it out. Now, if you're taking something that's too large and you're tapering it down, that's a much easier process than if you're trying to make something larger and cut plates to fit perfectly. And then you have to worry about the weld penetration on the inside. And there's just all sorts of problems. So if you can find an extrusion that fits what you need, that's going to be the best way, and it's going to give you the best chance of having a good sealing intake. The next thing that we need to think about are injector bungs. So depending on what size injector you want, we have to think about things like the attachment of the positioning and the attachment of the injector bungs, where the fuel rail is going to bolt on, and so on. I'm not going to get real deep into the topic of worrying about the specific position for bolting a fuel rail down, because honestly, if you go this far in designing an intake, you're probably going to be making your own fuel rail. There's fuel rail stock that you can get. It's already the right size. You just have to drill it for your injector locations. And there are, of course, drill bits that are perfectly matched to not only drill, but also do the counter bore and seat for the O-ring. So all that stuff is out there and available, but we are going to be using these injector bungs and just sort of working on positioning them. And then you can see that they're set up for 14 millimeter O-ring or Bosch style injector. So pretty common stuff that you would find off the shelf. The next thing, again, to think about is if you don't want to do a D-shaped plenum, or if you don't have oval runners, well, just search around, look for different companies. This Verocious Motorsports is another company that I came across. Again, absolutely no affiliation with them. Use them or don't use them, it doesn't affect me at all. I just thought that they had a really good selection of parts for DIY builds. So they have a lot of different aluminum tubing. So you can see here a foot of this 4-inch aluminum tubing is 30 bucks. And that could be the perfect plenum. But we also have to really keep in mind where that's going to hit our throttle body plate. Now, if we go to something like a 5-inch plenum and we're using a 65 millimeter throttle body, the bolt holes are going to be inside of the plenum. And this means that the flange for the throttle body really needs to be thicker, and we need to use blind holes that don't go all the way through. Otherwise, you're going to start to get sealing issues with the threads, because the threads on a throttle body are just going to be standard threads. They're not tapered. They're not meant to seal. So then you're going to end up with putting RTV or some sealant on the threads, and they're going to be hard to remove. And it's just a mess, and it's not something you really want to deal with. But we could go with a 4-inch plenum, and then we can use a reducer. In this case, they have 4-inch down to 3.5, and 3.5 will fit just inside of the bolt hole pattern of Ford 65 millimeter throttle body. So again, if you're using a bigger throttle body, bigger plenum, bigger plate, these are different things that you have to consider when you're talking about building these parts. So keep that in mind. One other thing that I thought was really nice about this RMR company is that with this manifold, they also have things like end caps that are already tapped and ready for things like a map sensor, air temperature sensor, and so on. So do some searching around, figure out what you need for your project and what's available out there, because it can honestly save you a ton of time by just purchasing some stuff like this extrusion for the plenum, and then you don't have to worry about fiddling with all the other little bits and pieces. You don't want to have to go through and make injector bungs if you can buy something off the shelf that already is ready to go, and you don't have to worry about things like injector leaks. So now that we've got some of the parts out of the way, and again, this is going to be the first intake that we're looking at, and this is going to be essentially the most DIY friendly version. So now that we've got that sort of set, the next part is to start designing the plenum and designing the runners. So we already know that we're going to be using that D-shaped, that 5-inch, but unfortunately on the RMR site, they don't give you an exact dimension or specification for the plenum. We know that it's a 5-inch diameter, but we don't know where that flat comes in. So we're going to have to estimate. And again, as long as you build this stuff parametrically, then it's going to be easy to update. Once you get the actual parts in, then you can make your decisions. With a build like this, the plenum won't really affect us, at least the plenum shape, if it's a little bit different, won't really affect us if we're going to have the throttle body plate cut and if we're going to have the head plate cut. Now, it will affect us if we're trying to make the throttle body plate perfectly fit that D shape. And in that case, I would suggest buying the parts first, like the plenum, and then making sure that it exactly matches. But just like before, I want to continue to use components in Fusion 360. So I'm going to get started by creating a new component. I'm going to call this one Plenum. And again, we are going to reuse some of these parts when we go to start building the next iteration, which will be a bent sheet metal plenum. And we're also going to go a little bit crazy. The plan is to go to a full CNC multi-piece part. One other design decision that I didn't mention is we could create another plate on the other side of the runners, and that other plate could serve to bolt to the rest of the plenum. It's kind of an in-between, or it could weld to it as well. It's kind of an in-between between going full CNC where all the parts bolt together and actually doing a welded manifold. But again, it's a little bit past just the base DIY that I want to talk about. All right, so now that we've got the plenum, I want to make sure that it's active. And I want to take a look at its origin. I want to figure out where that is. And it's going to be based on the default origin in the design where everything else is based. Now, this plays well for us in one regard, but it's also going to be problematic in another regard. And we have to think about this at this stage. And what I mean by that is the mid plane, or in this case, the YZ plane, is exactly in the middle of the manifold. And that's perfect. It helps me understand exactly where the profile of my plenum is going to be. The negative of this is that we can't really design about the origin. And the reason we can't design about the origin is because it's in the middle of this plate. Now, there's a couple things that we can do. We can not worry about that at all. We could just design out in space, kind of like we did with the throttle body plate. But if you have a little bit of OCD, or if you really want to take the time to make sure all of the origins of your parts are in the center of those parts, then there is a way that we can do that. So what I'm going to do is I'm going to go back and activate the top level, but I want to make sure that I have the origin of the plenum visible. So you can see that we can turn that one on and off. And right now there's no geometry to grab onto. If I select the plenum and I go to move, I am able to move that around. And what this will do is it'll reset the coordinate system for me. Now the trick to this is we don't want to move it at all in the X direction because we want to make sure that it's centered about our plate. The manifold plate was centered about the original origin, and we want to make sure that we maintain that. But we do want to center it about this plate here. And the way that we do that is we use our references, and there is a point-to-point or a point-to-position option. Now, when we do a point-to-point or point-to-position, it's going to move in all three directions, and it's something that is a little bit tricky. So there is another option that we have, and that's called align. And when we use align, we want to use components and select the from and to. Now, when we do the from and to, I'm going to hide the head flange for right now. And notice that I can select an axis, I can select a point, I can select a plane. When we select a point, notice that there's an icon that's displayed on the screen, and that was going to let us know the orientation of the Z axis. So you can see right now Z is pointing up. If I hover over this plate here, you can see that it's going to be pointing in a different direction, and that does matter for us. But what I want to try to do is I want to try to select the X axis, and then I want to select the circle or the opening for our throttle body plate. And what this should do is it should move the coordinate system relative to that. Now, you'll notice that it looks like it's twisted a bit. It's a bit off. And that's because this plenum isn't necessarily in line with what we're doing. So what I'm going to do is I'm going to cancel that second selection. And instead, I want to select this inside face and see if this gives us a different result. When I select the inside face, again, notice that it's sort of coming off in space here. Now, sometimes you want to make sure that you do have perspective with ortho faces turned on in your view. It can be easy to accidentally hit a shortcut key or to click on the camera view perspective and then not exactly know where this is. And you can see now we can see all the bolt holes. We're not obscuring any of the design. So all that looks good. And this tells me that this is centered about that throttle body plate, but it's still in line with the head plate. So if we bring the head flange back and we rotate this around, you can see from the front view, it's still in line there. It just happened to move it up and to the correct location to be centered with my throttle body plate. Now, as long as you are on an orthographic view or perspective with ortho, then you should be able to select the edge or the inside face, but just make sure that you do view it from that direction and make sure that you do have an orthographic view to ensure that it's in the right location. Last step, we want to make sure we capture the position and say okay. Now, if we go back and we activate our plenum, our coordinate system is still in the middle of our plate, but it's centered about our throttle body. Now, again, this step isn't necessarily required, but it's always good to design about the origin because it helps you work with symmetry. So I do suggest that you go this extra step, especially if you're thinking long term and you want to adjust the design or make changes downstream, or potentially reuse any of these parts. Designing about the origin can help make it easy to align it to other stuff in the future. So now that we have the plenum, I'm going to hide the origin and I'm going to start a new sketch. I'm going to select my YZ plane, and then I want to create my 5-inch D-shaped plenum. Notice that my throttle body itself is slightly above where the origin is, but remember that the throttle body, we're really looking at centering it about the runners, right? So what we can do is we can select some geometry, for example, one of the edges of this, or let's go ahead and just select that, the bottom, and maybe even the top up here where the injector bung is going to go, and then we're going to project that. So we're going to go to project, include, and project, and we want to make sure that the selection filter is based on specified entities. We don't want to bring in the entire plate. And what we're going to do is we're just going to include some of this geometry, and we're going to say OK. The reason that we do that is because now we have some reference for where the middle of that plenum is. So if we use a reference line, which again isn't needed, it's kind of an extra step, but if we use a horizontal reference line, we can now see where the middle of our intake runner is going to be. I'm going to convert this to construction, but this helps us understand where the flat spot of the D plenum needs to be. So I'm going to get started by drawing a vertical line. I'm going to hit escape, and then I'm going to use my midpoint constraint for that line and this endpoint. And this is going to be the flat spot on the D plenum. I'm going to hit escape again, and now we can move this around, we can increase it or decrease it, but its midpoint is there and it's a vertical line. This means that my plenums, or the runner from the plate to the plenum, is going to line up. The next thing I need to do is create that 5-inch diameter circle. I'm just going to do it off in space somewhere. I'm going to type in 5 and IN for inch. And now I've got this 5-inch plenum. Now, in order to line this up with the D, I'm going to select an endpoint, control select the circle, and say coincident. Even though it's not necessarily needed, I'm going to repeat the process down here. We could work with symmetry, taking this line and extending it all the way to the center of the circle, but we need to make sure that we have this D shape here. So now we have a 5-inch diameter plenum. We have this flat spot, which we haven't decided how big or small that needs to be. And again, we don't have the information directly from R&R. We would have to email them, give them a call, or purchase the part to get an accurate dimension. But again, it's all going to be parametric. We can change it later if needed. So I'm going to use my dimension tool, which is D on the keyboard, and I'm just going to determine that this is 75 millimeters tall. I'm making an arbitrary assumption just based on the picture. I think it's about 75 millimeters. If we bring the website back up and we look at it, we can see here about where it cuts through. And if we wanted to, we could bring that picture into Fusion and sort of get an idea. I think that's probably about right. I am going to use the trim tool and get rid of this stuff here. Notice that it gives me a warning for constraints, and that means that some of this stuff is likely able to now change. It can probably move around more than we want it to. But that's okay. It's not fully defined yet. We just need to make sure that we've got the 75 here and we've got the diameter here, which again is 5 inches. I just typed it in, and this is a metric design, so it automatically displays it in metric units. Now here's the other trick. The throttle body plate is sitting fairly high, and it's not going to line up with the plenum. Now, in reality, that may or may not be an issue, but there are some things that we need to worry about. If we're going to use a 5-inch plenum, then we have to worry about those holes. And I mentioned that before. If you're using a large diameter plenum, the throttle body plate might need to be a little bit bigger so we can have blind holes instead of going all the way through. Or then you have to start to worry about sealant and getting an air leak through the bolts. And that's not something we want, especially if we're talking about a boosted application. It will find any and all pinholes and areas to leak, and we don't really want that. So what I'm going to do, once I decide where this needs to be horizontally, I'm going to move the throttle body plate down. Again, we're talking about a parametric design. These are all decisions that are very easy to do. So once I'm happy with its location, I want to make sure that it's roughly centered, and I'm not super concerned with it being centered. What I can do is I can take the center point of the 5-inch diameter and I can control select the center point or the origin of that plane, and I can make them vertical. It automatically centers it for me, and then I can finish the sketch. Now, you might be thinking, well, it's solid. We didn't actually make a thin wall. Well, in Fusion 360, when we extrude, we can determine that we want this to be a thin extrude. And when we start, we can determine what that wall thickness is going to be. Now, I think the wall thickness of these parts is an 1/8 inch, so I'm going to type in 0.125 IN, which is about 3.1, 3.2 millimeters. Then we need to determine the length of it. So we're going to drag this out, and I'm going to set this to 2 sides. We could set it symmetric, but I want it to go at least to the back of that plate, and then I want it to come all the way up to the throttle plate. Now, if I wanted to exactly match where the throttle plate is, I can use the option to go up to an object. So we're going to select to object and the back face of this. Now, I do want to caution you here because I know we're going to change the back face of the throttle body. We're going to add more material so that it fits in the plenum. So selecting the face could be problematic because the references might break later. So the best option is to go to the construction folder where that TB plane was created. The TB plane was the one used for that sketch and that extrude, and just select the plane. Now, selecting the plane means that if we change the throttle body plate, delete it, get rid of it completely, it won't matter as long as the plane reference is still there. And that's really what we want to do to make sure that we have a good selection process. So that looks okay. I'm going to say, all right. I'm going to go back to a left view, and I want to go back and change the position of the throttle body plate. So I'm going to activate the throttle body plate, and I want to take a look at the sketches that were used to define it. Remember that the 65 millimeter TB sketch had a vertical offset. I'm going to right click and show the dimensions, which allows me to modify it without editing. And this vertical distance here is what controlled the height of it. So I'm going to change this to 25 millimeters, and it goes a little bit low, so we'll set it at 30, and it looks like it puts it in a pretty good spot. Another thing to keep in mind is that this plate right now doesn't match the outside shape of the plenum. And that's okay, it doesn't necessarily have to, but we do need to cap off the plenum. So there are two sort of schools of thought or ways that we can think about this. Depending on the tools that you have available, it might be easier to have a plate cut to cap the plenum off just with a hole in the center for the airflow, in this case 65 millimeters, and then a second plate for the throttle body that we can weld on top. And that prevents us from having the air leak through the threads, but still allows us to easily drill and tap all the way through to get clean threads to the end. You do need to be extremely careful that you don't use too long of a bolt to go all the way through that plate, because then you'll start to push into that material and potentially break or crack it. So again, that's probably the easiest way from sort of a hand fabrication standpoint. You will notice that there is a weird sort of line in the middle of this. We'll talk about that in just a second, but it does look like the inside and the outside are slightly different. So we do want to make sure that we check the wall thickness of both of those. But the throttle body plate does need to be addressed. I'm not going to worry about it just yet. I think that the method I'm going to do is by capping off the end of this throttle body, or capping off the end of the plenum behind the throttle body. So I'm going to go back to the plenum. I'm going to go back to that extrude. And instead of going all the way or going directly to that plane, which is the to object, what we're going to do is we're going to add an offset for the thickness of the material, so that way we can make a cap that fits there. So my offset value, I'm going to enter a positive value of 0.125 inches, and notice that it gives me a gap. So if we look at this from the back, you can see that we've got that gap, which gives me enough room to do an 1/8 inch wall plate, which is the same, the assumed thickness of the plenum. And that way the throttle body plate is still in the right location that we're designing it. Now in reality, the throttle body plate moving an 1/8 of an inch isn't really going to make that big of a difference. But if you are tight on space and you are trying to get things very precise, then these are the things that you want to make sure that you adjust. So we can see in here that when we use a thin wall and 2 sides, we don't use the symmetric option, that Fusion 360 gives us the available option to change the wall thickness in the other direction. So we do want to make sure that this is 0.125 inches. That will make sure that we don't have a weird seam or step in the middle. Everything is now nice and smooth. So let's take a look at what we have so far. We've got the plate at the head, we've got the throttle body plate, and we've got the plenum, the D-shaped plenum. Now the plenum obviously needs to be capped. On the back side is probably, if you have the room, where you would put your ports for things like the air pressure sensor, and things like air temperature sensor and any other vacuum or ports that you might need. Right now, I'm not going to worry about that. We're going to go back and forth and jump around and cap that stuff off. But right now, I want to focus on the runners. But we haven't saved in a while, so let's do a quick save, make sure we don't lose anything. So the runners could be their own component, or we could assume that they're part of the plenum. In reality, all of this stuff gets welded together, so how you break it up kind of just depends on your own workflow. I'm going to continue to work directly in the plenum component, and I'm going to include the runners in that. And part of the reason I'm doing that is going to be partially because these would be off-the-shelf components we would buy from this manufacturer, so organizing them into a single component kind of helps me sort those things out. And another reason is just because, again, everything is going to be welded together. So we could have done it all as bodies. We could do components for each section of the design. But ultimately, if you're working through a design and you're configuring things like components, a good way to think about this is if any of the parts need to move, they need to be separate components. So if you have any mechanical motion that you want to account for, say a throttle body with a butterfly in the middle, those would be individual components. In this case, breaking up the components by the plenum and runners is an important step because we are going to be looking at designing other manifolds. So I know that the plate at the head is going to be its own thing. The plate at the throttle body is its own thing. And we're going to be swapping out the intakes a little bit. We are going to do a bit more with this plate at the head, but because I know that we're going to be swapping out the plenum and the runners, it's kind of why I'm breaking it up here. But again, it's important to just know that this workflow doesn't necessarily mean that it's universally the workflow that you should use. There are variations that you can make depending on your requirements. So let's get started by creating a sketch. And we want to create our oval runners. Now, if we want to bring in a reference from the plate, we can go to the head flange sketch, and we can use this to bring in our new reference points for our slot. So we can go to Create, Project Include, and Project, or use P on the keyboard. I'm only going to do this for one of them because we're going to create a pattern for the rest. So I'll bring those in, I'll hide the sketch, and then we'll go to Create, Slot, and we can do a center slot. So I'm going to go from here to here, and remember that the oval runner that we can get from that company, assuming this is exactly what you're building, was a little bit larger. So it was 30, almost 32 by 54. So when we think about this, we need to go to, let's say 32, and you can see the size that it is right here. So once again, depending on what you have available, you want to make sure that you size it appropriately. I'm going to go a little bit larger. I'm going to say 34 millimeters, which exactly matches. Again, keeping in mind that I'm not planning on actually producing this manifold, so I'm just going to use the numbers that we have. We could do a thin extrude again. We could also do an offset here, so we have the close profile that we need. And it's going to be 0.125 inches or that 3.175 millimeters. So again, you can use either or, it'll automatically convert it for you. We will have to handle or deal with the injector ports, something that we're going to come back to. So just keep in mind that we will deal with that depending on how we end up doing the injector bungs. But for right now, we just want to make sure that we create this. We're going to do an extrude. We're going to go from here. And in this case, what we want to do is we want to go a distance to object, and we're going to select the flange itself. Instead of joining, I'm going to create a new body, and we're going to have as many bodies in the component as we want. Part of the reason is I don't want to join it to the plenum yet. In reality, I need to keep them separate. They will be manufactured separately. In CAD, we can join them and we can split them later if we want to, but right now it's just easier to create a new body. So this is an individual body inside of this component, which means that they move together. They still share the same coordinate system. I could create components inside of this plenum if I wanted to, but for right now, I think that's going to be a good option. Also keep in mind that we did create a pattern for these, so we can use a linear or rectangular pattern. We can select bodies because we created the intake runner as a body, and we can select the direction along the x-axis. We need to have 4 of these, so I'm going to increase the number to 4, and we need to make sure that we have the appropriate spacing. Now, if you don't remember what the spacing was, we actually have 2 options here, extent and spacing between. We can always bring back our old sketch, or we can always come back and adjust these values. I believe it was 85.5, might have been 86, so let's enter 86. And again, we can always come back and adjust these values. 86 looks like it matches, all of them seem to match up, so I'm going to say okay. And now we've got the 4 runners there. Again, we will have to take care of the injector bungs because those are open, and we will have to open this up inside the plenum. There are a couple of different ways that we can open that inside the plenum. What I want to do now is I'm going to rename body 1 to runner 1. I'm going to rename the other bodies runner 2, 3, and 4. Just to make sure that it's easy to keep up with. And then I'm going to hide them. I also want to bring back this sketch, do a quick save, and then we'll pop the holes in the plenum. All right, so let's go ahead and extrude the inside. And we don't want to go through everything, so again, I'm going to use the option to object and select the inside face of the plenum. Now, the reason I think it's important and that we take the time to make these selections and go to objects is because if we happen to make the plenum thicker, or we move it further away from the manifold, or we make any changes like that, then everything is going to update properly. And that's the basis of a parametric model, to make sure that everything does update when you make changes. So from here again, we're going to do a rectangular pattern, but this time a feature. Select the extrude, select the direction, again the x-axis. We're going to do 4, so increase this to 4. Change it to spacing of 86 millimeters. So that should perfectly match up with the ports, and that should also match up with all the runners. So keep in mind that we matched the inside of the runner to the inside diameter of the runner to the opening that we popped into the plenum. And that's what you would want to do. We're going to keep the wall thickness the same, which means that when we're welding, that we can use equal amounts of heat. This is going to be a tricky part to weld, just simply because of the space between the runners. It becomes tricky because you can go ahead and weld completely around the first one, but then the intersection between 1 and 2 is going to be tricky. Weld completely around the second one, and you're going to have that issue at both sides. You're going to have it at the plenum, and you're going to have it at the plate. But again, that fabrication aspect of it is just going to be sort of part of the process, something you have to figure out. So from here, the next design decision is, how do we deal with the injector bungs? Now, in some of these cases, if you are doing a CNC plate rather than a water jet or a laser cut plate, then you can just actually machine in those details. It will require a custom fixture at a certain angle to get that to be cut. But in a lot of cases, if you're already doing things like doing a rounded entry or a ported section, you port matching it to the head, you might be able to include all that machine work at the same time. What we're going to be doing is we're going to be doing a weld on bung. And the thing that we want to consider with the weld on bung is going to be how we're actually going to manufacture it. So when you create these designs in 3D, it's very easy to create something that is either very difficult to manufacture or in some cases impossible. So we need to be really mindful of that. So I'm going to go back to the website and I want to take a look at the injector bungs. We can see here they are welded at an angle directly to the runner that they have going into their plenum or their plate. And they just look like tubes. So when we're doing the design in 3D, if we know that we're going to be using off-the-shelf injector bungs that already are pre-set up for whatever injectors we're running, we don't really need to worry too much about all the internal details. If there's a step for the O-ring and the seat, all we really need to do is we need to worry about how much material we have to work with, 2 inches, and what the diameter of this is. In this case, it's 3/4 or just above 19 millimeters. So that's going to be the starting point, 19 millimeter diameter, roughly 51 millimeters long, and that's going to be the part that we use. Again, if you do have certain injectors and they have certain criteria, for example, how far you need it to stick down into the head plate or the port, then that's something that you want to account for with how you make these parts. And all that information is available online. Obviously, if you have an injector to measure, then you can figure that out. But the main thing that we're going to do is we're going to design that injector bung at a 45-degree angle. We want the injector to be pointing into the port. And because we already have this section here where it's raised up that matches the port on the Honda head, in reality, what we would want is this section to be up a little bit higher than the one that's matching the head. And we would want the injector to be pointing in there. It's a little bit trickier for us to do on a DIY setup because we just have fabrication constraints, some things that are just harder to do. So I'm not going to go too deep into this topic, but we're just going to talk about different ways in which we can set up the references to model that geometry. So one of the ways that we can do this is to create a reference sketch, and that reference sketch will be able to create a plane. Another way that we can do it is we can just create the geometry and move it into the right place and then subtract it away, subtract the overlap away from the other bodies. But what I want to do is I want to create that sketch reference. And the reason I want to do that is because that'll give me the available option later on to change the angle. So we're going to create a new sketch. I'm going to use this, again, the same side view. Now, if you accidentally select something like the end of another body, it will automatically bring those in. And you can see that my sketch is on this face. So I'm going to use Control Z and undo. And I want to hide the throttle body plate. I don't need to see it for this. And I want to make sure that I'm actually selecting a plane that belongs to this component. And then the next thing I want to do is I need a reference. I want that point right there. So I'm going to use P on the keyboard, which is project. You can also go to create, project, include, and project. And I just want to bring one of these points into my sketch. Now, the reason I want to do that is because I want the injector bung to be completely centered upon that point. So then I'm going to use a line, and I'm just going to drag this line out, and then I'm going to drag a horizontal line as a reference and hit escape. This is going to be a construction line. It's just there so that we can define an angle. And then we're going to use the dimension tool, which is D on the keyboard, to do 45 degrees here. And then we need to determine how long this line is going to be. So remember that we have about 2 inches or a little bit over 50 millimeters. So what I want to do is select that. I'm going to right click and say aligned. I want to only dimension the length of that line. And we can determine how far away that injector is going to be. Now I'm going to set mine at 15 millimeters, knowing that I have this large plate that the injector is going to go into. But keep in mind that the spray direction, the point at which we're spraying the injector, is really going down. It's going to hit the bottom of the port and not the back of the valve. So again, these are all things that you need to consider if you're designing something. It might be beneficial to maybe put an injector on the bottom or try to change the angle. And again, that's all stuff that we can do parametrically. I could say 30 degrees and do a really steep angle here to get the injector to spray closer to the back of the valve. So those are all things that we want to think about. Now, that's just kind of sitting out in space. It's really not referencing any of these ports, but that's okay. What we're going to do is we're going to finish the sketch. We're going to go to construct and create a plane along a path. This allows me to select the line. I'm going to pull this all the way to the end, which is 1.0, or the total distance of that line. And that means that my new plane that I created is referencing that. Now, one of the sort of tricky parts here is that the center point or the origin of this new plane is going to be that point on that line. So if we happen to be able to put that origin plane somewhere sort of in the middle of these runners, then it would automatically line up. That's not going to be the case for us, but that's okay. We can fix that. But what I want to do now is I want to create a new sketch directly on that plane. I don't want to worry about the center point, so I need to come over here. And what I want is I want to find a reference that I can use. So again, P on the keyboard to project, and I'm going to bring in this as my reference. And I also want to bring in this edge as my reference here. And I'm going to say OK. Now the reason I want to bring those in is because now I can go and draw a circle at the midpoint of this edge, and I can figure out the diameter. Now remember, it was about 19 millimeters. If we go back to that website and we look at the drawing, 19.05 millimeters is the outside diameter. So in Fusion, we need to make sure that outside diameter fits within the confines of our plate. Now, if we have to go back and change the opening for the injector in the plate, not a big deal. We can always, again, use some hand tools and port it to make sure everything fits. The injector likely is not going to stick through all the way into that section, but we need to make sure that at least we have material there. If these two edges happen to coincide or be really close together, when we go to weld this, you might have an issue where you actually burn away material because you've got an 1/8 of an inch or however thick these are going to be. You've got that much material, and then you end up having an issue where this sort of melts away. So all things that we need to consider and think about. The other thing that I want to do here is I want to create another circle, and I assume that the inside of this is going to be somewhere in the 13.5 to 14 millimeter range, just because it's the standard size for the injector. So I just want to see where that falls to make sure that, again, it lines up okay, because we are going to be welding around everything here. Another thing that we should think about is when we look at this, it's going to become problematic if we try to extrude it up to something if there's nothing there. So it could be a problem, but let's go ahead and give it a shot. All right, so from the left-hand side, this is going to be a portion of the injector bung, and then we can determine how far out from there it can extend. If we want to make any changes at all, we can make those changes to the reference. In this case, I'm going to show the dimensions for my reference plane. Now, if I increase this to, say, 20 millimeters, even though that is in the middle of the entire part, because the plane that we created is referencing that endpoint of that line, it's automatically going to move this away. So again, 25 millimeters, and again, it's going to move the whole thing away. I did mention at the end of the first video, under Modify, we've got change parameters. And using the change parameters for values you know you're going to want to configure, things like the injector angle or the runner diameters or things like that, putting all those in as parameters at the start can mean that your design is really flexible in regard to making changes or updates. So if you are doing a lot of flow testing, if you're building some of these designs, maybe you're 3D printing them and you're doing some flow testing or something like that, then you can make those changes and you can see how it affects things like the injector spray pattern, where it's hitting the valves, because we don't have a good idea of where the back of the valve is in this relationship here, because obviously I just took a picture of a gasket. I don't have a head that I can reference and I can look at, just pictures on the internet. So these are things that you might need to play around with and adjust. And just like that, with the distance, we can change the angle and we can move that injector bung up or down. We can make those changes by just adjusting those dimensions. So that's why it's really important that we think about the parametric nature of all of these different pieces we're putting together. Now that we have that, I'm going to go ahead and do extrude. I'm going to select this geometry. And as I select this geometry, as I bring it down, you can see it starts to cut into the intake runner, and it starts to cut through that plate. Now, in reality, what we want is this solid body to perfectly match the outside, and then we're going to have to cut away the inside, and we'll do that by extruding out the center. But let's try to use the to object option and extrude it down to just the top of the runner. You can see that it comes inside of here, and obviously that's not what we want, but that's okay for now because we're going to go back and we're going to cut it later. So what I'm going to do is I'm going to say new body, and I'm going to say okay. So when we look at this, the main thing that we want to see is that it enters at least underneath that opening that we have for the injector in the plate. Now, if that's okay, then what we can do is we can use something called split body. And with split body, the bodies to split will be this injector bung, and the splitting tool is going to be the face of my plenum here, or the face of my plate. And that's going to allow us to break that up into two different pieces. And then the little piece, that small piece, I'm going to right click and remove it. So now we've got this injector bung that is going to be an off-the-shelf part, and we just need to cut it. Now, if we're doing 30 degrees, then we cut it at 60 degrees on the bottom and 30 degrees on the top. If we're doing 45, obviously we just cut off 45 from each side. But that helps us build out that little piece. The last thing that I want to do is I want to get rid of that section of the runner. So I'm going to bring back that last sketch. I'm going to select the inside, and I want to extrude that down. Now I'm going to extrude that, but I need to make sure that I'm only cutting away from the actual runner. And we can do that by selecting Objects to Cut. Because we renamed it Runner 1, it's very easy to know that we only want to cut through that runner. Now we can hide the sketch, and we can create a rectangular pattern of this body as well as the feature. Now they have to be done at 2 separate times. The way that we could get around this is if we did all this work to one runner, and then we went back and we did a pattern of the bodies of the runners with all these features created. But again, these are all the decisions that you need to make along the way and how they affect the design downstream. Now, creating these extra rectangular patterns is not really going to affect the design other than the fact that we're going to have more features in the timeline. So we're going to do first the features, and I'm going to use the extrude cut. The direction is going to be along the x-axis again. We're going to do 4 instances, and the spacing is going to be 86 millimeters. Now that 86 millimeters comes up a lot, so that's one of those values that we could create as a user parameter and link it if you were designing multiple intakes and you wanted to do things like account for different runner widths. Intakes are not really that configurable, so I'm not too worried about that value, but just keep in mind that we could do that. So you'll notice that that feature didn't work. Now, part of the reason it didn't work is because we're trying to pattern a cut along other bodies. Sometimes what we can do is we can change it to optimized, and we can allow it to make that cut. You can see here that it didn't work again. So what this tells me is that this feature is ultimately not going to work. And what I'm going to end up doing is I'm going to go back and I'm going to delete the pattern that was used, or at least move the pattern that was used for that body. And if I can drag that all the way to the end, then it's automatically going to include that cut. And because we are patterning a body, what we can do is we can include this body in that. So we're going to hold down Control, select that body, say OK. And now we still maintain the runner renaming, and we can go back and we can rename INJ1, and then I'm just going to rename each of those as well. So INJ2, 3, and 4. And that way we have the injector bungs and we have the runners. And we didn't really have to do all that much extra work. So sometimes when you're creating patterns, the adjust, identical, and optimized, if you're creating a pattern of a feature that's cutting through a body and trying to pattern that feature across other bodies, one of the easier ways to do that is to use the face option. Select the faces that you want to pattern, and usually that's a little bit more robust than the features. But again, in this way, because we already had to create a pattern of the runners, it just made sense to drag that feature to the very end, and then it's already accounted for. Remember the cut for the plenum, that was taken care of with a different feature, so we don't have to worry about that one. All right, so at this stage in the game, we've got the runners, we've got the injector bungs, we've got the D-shaped plenum. I didn't add a fillet to it, and because this is an off-the-shelf part, I'm not too worried about having a perfect match, but you could certainly go back and you could use F on the keyboard, and you could add a fillet on the inside and then a fillet on the outside. When you're using fillets in Fusion 360, you can do multiple radius or radii fillets by hitting the plus icon. In this case, I just did 2. It really ultimately isn't going to matter, but that way we just have a little bit of a rounded edge. Now what we need to do is we need to cap this off. I need to cap it off on the front and cap it off on the back. So what I'm going to do is I'm going to select the back face, create a sketch, and then I want to think about how this is going to work. So when you're welding parts like this, a lot of times it makes sense to do an offset of the outside. Now in this case, I'm going to go in half the distance, minus 0.0625 inches. And the plate that I get will have a small lip here. And that helps me when I'm welding plates together like this, the 1/8 inch plates. If they line up perfectly and butt together, then the weld is going to build up on the outside of it. And then you're not going to get the same level of penetration. if we have this little bit of a gap here, or a little bit of an offset here, what ends up happening is that gap ends up melting together and the weld is a little bit cleaner around that corner. So I like to do that when I'm creating parts that are going to be welded. Might just be a personal preference, but that's the way that I like to do it. So what I'm going to do is I'm going to extrude this 0.125 inches again. And again, this is going to be a new body. So that's the cap on the back. I can reuse that same sketch. And ultimately what we do need is a hole in the center. So we can right click and edit this sketch. I can bring back the throttle body plate and I can project that hole in the center. I can also make it a little bit larger. That way, if we ever happen to use a larger throttle body, then we can simply do that. So in this case, I'm going to say 70 millimeters. I'm going to select this inside one, turn it into construction, and finish the sketch. So that sketch now includes a hole in the center. And that means that if I reuse it, so if I say extrude, I select the profile that I want. I'm going to hide this last body here. I'm going to select the profile that I want. But this time, instead of starting from back there, I'm simply going to say start from object. It's going to be this face here. And then it's going to come out in this direction. So it's going to be minus 0.125 inches. And again, it's going to be a new body. And this time it's the same exact sketch and it's just used at a different reference. And again, because we used from object, we selected a reference. If the plenum size happens to change at all, those plates are going to change with it. Let's do a quick save and then let's just test that theory. So the original plenum was this extrude here. So if I edit that feature, the first direction here again was offset from the back of that throttle body plate and it was offset a distance of 1/8 of an inch essentially. So what we did was we created an offset. If I increase this to 0.75, actually it's thinking it's 0.75 millimeters. So if I increase that to 0.75 inches, let's go ahead and put that at the end. And I say, okay, you can see that the plate is still in the right location. I'm going to do Control Z to put it back where it was, but that just shows you that using those references, creating a sketch on a face means that if that face moves, the sketch is going to move with it. Or using from object or to object in your extrudes means that you're maintaining that parametric link. Now our throttle body plate can go on the outside. We can weld it exactly where we want it. We can determine if we want to use a larger or a smaller throttle body and make those adjustments. Of course, you could create a plate that exactly matches the plenum and have the throttle body holes in it. But remember that we do need to be careful about having those holes go all the way through. We want to make sure that we have a blind hole so we don't have air or a pressure leak somewhere. So this brings us back to another aspect of this. I'm going to do a quick save. And again, it comes down to how much we can update this design. Now the entire design, the head flange is based off of the default origin and that picture of the gasket. The throttle body position is based off of a couple sketches. So what we did was we used references for the center location of the plenum based on the location of the ports for the runners. The throttle body plate, we ended up moving down so that it fit, but it's not parametrically linked to the vertical position on the plenum. That can move up and down. Because we projected the center hole location of that hole on this plate will move with it. So we can do a test of that. We can take a look at our references and we can see how things change. So this 30 millimeters here, if I change it to 50, you can see the hole in the plenum changed with it. It moved up simply because we use that projected reference. We don't want it there, but again, if we took it down to the bottom side and we hide this, you can see that it moves down as well. And if we put it back at 30 millimeters, it should be roughly in the center where we had it. Some other aspects of this is the reference plane. We decided how far away the plenum was going to be at 150 millimeters. Let's change this to 100 millimeters, and you can see that the plate moves in, but the plenum itself wasn't defined based on the center of that plate. So this is a case where we don't maintain a parametric link between the throttle body plate and the plenum location. If we go back to the plenum and we take a look at the original sketch and we edit this sketch, its center location was vertical relative to the origin of this sketch. Now that vertical relationship means that it's going to be fixed relative to the sketch plane that we used. Now, it's relative to us moving the coordinate system. Remember initially when we started, we moved the coordinate system point to point or aligned it with the throttle body plate. Now the trick with that is moving or aligning something to the throttle body plate is not a parametric link. While it's temporarily moved to that location, it's not parametrically linked to that part. So if we decide to move it later, then it's not going to update. The way that we fix that is by deleting this vertical relationship and then projecting this reference. So projecting something from the throttle body or from the sketch that's used to define it. So projecting in that reference and using that reference as our vertical relationship will mean that the plenum can now update. We do have to be careful because that is actually over the origin. So what we want to do is we want to hold down the left mouse button and make sure that we look at the sketch point as our selection, and then we can control select the center of our circle and we can put them in the same location. We can also make sure that the plenum and this is concentric. So if we want to maintain a concentric relationship with the center of the throttle body in this, we can select both of those and we can make them concentric. Now, there are going to be some cases where you can't actually solve that. And the reason that we can't solve that in this case is partially because of this midpoint relationship. So that midpoint relationship means that the throttle body can move up and down, but unless it happens to be exactly in line with that, we can't have a concentric relationship. So again, these are all things that you need to think about. For this case, what I'm going to do is a vertical between the center point of my throttle body and the center point of the shape of the plenum, that 5-inch diameter. And now with that sketch updated and configured, if I move this to 100 millimeters, everything should move with it. So if you run into this problem, you have to really think back to the steps along the way, where we defined those references, how we were putting pieces together, and whether or not we're just temporarily aligning something or if we're trying to maintain a link or a relationship. Now, when I'm designing parts like this, I typically would put references where they needed to go, right? So if I needed the throttle body to be in exact position, exact orientation for intercooler piping or pointing it toward an intake, then that's exactly what I would do. I would define where that throttle body plate is, I define where the head is, and then all the rest of the stuff sort of is referencing that. And that gives you the ability to move things around and have your design update. Now, obviously, as the designs get more complex, this problem becomes more and more difficult. But that is the basic, the basic process to get this to work. There are other sort of design decisions that we would want to think about. If we need to taper the back of the plenum for a brake booster or something like that, then you would need to make sure that after you create the plenum shape that you cut, either extrude it away or use a split face, split body. And then when you create the cap, instead of creating the cap just on the end shape, you would do it based on the taper. You would select that cut face. So we can go through that process because that is pretty common. Let's go ahead and we'll tackle it real quick so that we know how to do it. So body 11 was that back plate. I'm going to go ahead and just hide that. I'm going to create a sketch from the top. I am going to use P on the keyboard. I want to project this point. And then I'm going to use a line. And the line is going to come all the way through. I'm going to create another line just as a reference. And the reason that I'm doing this is just so that I have something to define for an angle dimension. So we can dimension between these two and say that we need 130 degrees. The end point of this line doesn't really matter as long as it goes through the plenum. If you increase the plenum to an unreasonable size, then that line might not be long enough. If you really want to, you can define it to make sure that it stays well outside. And then what I'm going to do for this case is I'm going to use split body. Now, because we only have a single line, we have to use something like split body. If we were to draw a close profile, we could extrude it through and it would automatically remove that piece. The reason I'm not doing that is because I want to leave that piece in the design. And that is going to be, let's see, body 1 in this case. And now that we have the plenum cut at an angle, it's going to probably starve that fourth runner a little bit. It's just kind of the nature of the way that the air is going to flow. It's going to create some issues in this corner because it's now very tight, but let's at least look at how we would do this. So select the face, right click, create a sketch. Just like before, we're going to offset that profile. I'm going to come in a distance of minus 0.625 inches. And then we're simply going to extrude it like we did before. So we're going to come out as a new body, a distance of the 1/8 inch, 0.125 inches, and just make sure that it is a new body. So now we've done the exact same thing, except now we've capped it off at an angle. So I'm going to go back and just activate the top level, go back to an isometric view, and you can see now we've got our injector bungs, the plate, we've got the intake runners, we've got the plenum that's a D shape with this plate on the back, and we've got our throttle body plate on the front. That, at this point, it's what, 3 hours or so, but that is going to be the design of a basic intake manifold. Now, obviously, this can apply to whatever, in this case, 4 or 6 inline 6-cylinder car. It gets a little bit more complicated, obviously, when you go to a V-series motor or something like a flat motor in a Subaru, but the process is still the same. And the things that you really want to be mindful of is the parts that you can get off the shelf. So if you're doing a DIY intake, then you want to make sure that you look at the parts like the D-shaped plenum, the intake runners, the plate material, the injector bungs. Think about all that stuff that you can get, and then really put in the time to make sure that your sketches and your references are defined in a way that you can update your design later. If you decide to make the runners shorter or longer, you don't want to have to go back and fix a ton of stuff. In this case, I can just edit one dimension. I can say, well, I want a super long runner. Let's say I don't have anything in the way. I can just come back and I can make this 300 millimeters and everything moves with it. Obviously, that's kind of crazy looking, but those are things that you should really start to think about. Decide how long your runners need to be, how short they need to be, and then define everything so that you reference a handful of sketches or a handful of dimensions. Making sure that you keep those references very early in the design, like the location of the throttle body, the location of the plate, making sure that those are all, all sort of done in order will be very helpful. Another thing that we should keep in mind is the fact that we created these pieces as components, which means that I can just take this and move it away. And if I capture its position, it's not going to break my references. And the reason it's not going to break my references is because that is a feature in the timeline that happened after other things happened in history. So if I still say, make this 250 millimeters, the runners still update because all of that stuff happened back in the first couple of features in the timeline. The capture position happened very late in the design, so I'm still able to move things around, maybe add more geometry, maybe bend the runners in a different orientation or do something like that if I wanted to. Obviously, I don't want to do that, but just note that these are things that we can think about and the way in which our designs update. Now, at this point, I'm not sure when the next video is going to come out where we're going to tackle going into a more advanced intake, but I at least wanted to get these first 2 videos out to make sure that we understood the basic process. And the other ones, I'm going to focus more on things like the plenum design and less on the overall process of building all of the different pieces, because a lot of it is repetition. A lot of it happens over and over again in the same manner, but really we're going to focus on the way in which we can create more unique designs. I'll talk a bit more about things like hydroforming, at-home hydroforming. You can do it. It is kind of dangerous, but you could also create bucks and forms and hammer form the shape of the intake. So that's something I've done before for different body panels and parts, and not necessarily intakes, but it can be done there as well. And then we'll talk about the last version that I want to get to is CNC, where the runners, the injector bungs, all that stuff happens in a top and bottom half of the intake that bolt together. That one's going to be quite a bit more involved, but that is going to be essentially the end goal, something that we can look forward to where the parts are either bolted or potentially welded together. So if you have any questions on what we've done so far, please let me know. Leave a comment below. If you're working on something like this, a specific car or a specific design idea that you're having trouble with, please let me know. You can always email me, support@caducator.com. Thanks for watching, and we'll see you in the next one.